So hi everyone, I'm so happy to be here and thanks for joining in. Nikita, I've not seen such motivation ever in my life. Thanks for doing that. And so about me, I'm a second year PhD student at UCSD and I work on various aspects of trustworthy AI. One of them is explainability, the other is auditing and robustness. Yeah, and this is one of my latest works, and I'm very excited to talk about it. So I'll just go ahead now. By the way, here's my website. If you want to connect with me, you can find all the information here. So I'm going to talk about a framework for certified auditing of machine learning models. And we will begin with this is joint work with Mihal and Kamalika. Kamalika is my advisor and Mihal is my collaborator. So to begin with, you might have heard about auditing in terms of like tax audits and like account audits and so on. But auditing goes beyond just finance. So auditing is an examination of a process. It can be for a process in an industry or of an algorithm like Google's search algorithm, ranking algorithm, or in our case, it can be auditing of a model as well, of a machine learning model. So auditing is usually like how it is different from normal testing is that it's usually done by a third party. That's how it's different. And it can test for compliance with like government laws and policies and so on. But why would you need auditing for machine learning? So as we all know, machine learning models are a black box, and these days they're becoming larger than ever before. And people like us, like independent entities and small companies, there's just no chance that we will be able to train such huge models by ourselves. Like the field is also very fast moving. So I don't think it makes much sense to do that. So the trend is usually to have these large models built by large corporations, and then you use them for your tasks via fine tuning and so on. So like here, we don't know what's the nature of the large model, right? We don't know if it's fair, if it's private and so on. We just like use it. And recently there has also been a lot of false claims, like malicious false claims or like naive, unverified claims that people have been making about their models' performance and so on. And now we are at a stage where machine learning models are being used for critical, very, very critical applications. So government is going ahead and making a lot of policies and norms, like we had right to explanation and right to data deletion by GDPR and so on. So when you have all these policies and all these issues, you would want to test those models, right? But usually what happens is that these models are hidden, like they are black box to you, like black box not in explainability sense, but also in like access sense. You only have API access to all these. So that's where auditing comes in, because you are a third party now. You only have black box access to a model. That's the general setup. And like auditing has been looked on like in several papers before mine, but usually like now that auditing is becoming very crucial. So if suppose I audit Google's model and Google or some big company's model, and then I find that the model it does not follow one of the government laws, right? And then I as government can ask Google to like stop Google or a large company to stop using that model. And in that case, like the large company can question me back, right? Like, why should I trust you as an auditor? Like, what is your certification that you are providing me? And they can also sue the government and so on. So that's why the question is now, like, can the auditor be trusted? Can you build auditors with some certification or with some guarantees? And that's where some theory is going to help us. So that's the crux of the paper, defining some certificate or some guarantee and then designing auditors which will satisfy those guarantees. So you can trust the auditor in certain scenarios completely. So going ahead, I will define like what are the entities that I consider in an auditing process and the guarantee. So one of the most important entities is going to be the model that you are auditing, and the auditing property. So auditing property is like, what do you want to audit for, right? You could audit for data deletion, you could audit for privacy, you could audit for fairness, you could audit for accuracy, precision, recall, and so many things, right? So like theoretically, we call it an auditing property. And then we have a data scientist. So data scientist is like a company or an individual, anybody who creates the model that we are auditing and has white box access to the model. So this creator knows what are the weights of the model and so on. And for right now, we'll assume that the data scientist is truthful. In the paper, we consider scenarios where it is not truthful. And the last entity is the auditor. So auditor audits the model H bar for the auditing property, and auditor has query access to the model. So auditor can only do like API sort of queries, but cannot see the weights of the model. And the queries are sent to the data scientist who runs the query through the model and then gives back something. So it's like the access is through the data scientist. Yeah, these are the entities of the auditing process, and the model to be audited, like the H bar is fixed, right? So that's what I want to highlight. It's fixed, but it's like hidden from the auditor.
Chhavi?
Yeah.
Will it be okay if I ask a question?
Yeah.
Yeah, just curious, why did you assume that the query has to be routed through the data scientist and not directly call the API? Or do you think that when I call the API, that implicitly assumes that it's going through a data scientist because they can always fake the API? Is that the assumption?
Yeah, the latter case.
Okay.
Yeah.
Thank you.
You're welcome. Right. So now I'll define some of these entities more precisely. So the auditing property, we define it using a score function. Score function is a function that takes in a hypothesis from a hypothesis class and then gives a value between 0, 1. And this basically models like the extent to which auditing property is followed by the model. So if we consider fairness to be an auditing property, then how fair is the model is encapsulated in this by this S of H. And so like what exactly is the form of S of H will change depending on the auditing property. So if you consider accuracy, it can be like the number of correct predictions by total predictions, or it can be the loss function, or it can be like in case of fairness, it can be one of those fairness metrics and so on. So the exact form can change based on what it is. And yeah, one thing I forgot to mention was that the hypothesis class is known to the auditor. So like if it's a linear class, if your model is a linear classifier, or it's a neural network, or it's like a convolution neural network or an MLP and so on, is known to the auditor. And I think that's important, at least theoretically, like what kind of guarantees you can provide. Then now we will define our guarantee that we will use to design algorithms. So the auditor's response that the auditor gives at the end of the process, I consider it to be a binary variable, yes or no. And you could change it to other things. So this is the important part. I wish I could annotate. Yeah. Okay. Yeah. So this is the important part, which is an epsilon delta auditor. So we will define what an epsilon delta auditor is. So if suppose the score function is very high, like if the model is very fair, then the auditor should say, yes, the model is fair with a very high probability. And if the model is totally unfair, then the auditor should say that it is not fair with probability 1. So that is the kind of guarantee that we are defining, and we call it an epsilon delta auditor if it satisfies these guarantees. Yeah, is there any question about the guarantee? So next,
So, sorry, just to clarify. So I guess you're saying if you're claiming that their model is not fair in this case, you have to have it probability 1. You're 100% confident that it's not fair, but you're giving some like leeway or some flexibility, like maybe it's not fair by some epsilon, and so you have some lower probability, but you're not sure. So you have to be very confident if it's not fair. Is that what you're saying?
So between 0 and so if the model is totally unfair, then you know that it is, then you will say that no, it is unfair. Then if the model is if the model is more fair than epsilon, then you know that it is, then the auditor knows that yes, it is fair with a high probability. But between 0 and epsilon, the guarantee does not say anything. So we cannot say much.
I see. Okay, thank you.
Yeah. And so the guarantee here, like it depends on epsilon, right? Epsilon and delta. So based on how high the probability that you want to be, and what is so the epsilon, like the lower it is, the better, right? Because then you can tell if it's like only 50% fair, like only 10%. If you can say something about 10% fairness is better than what you can say about like 50% fairness, right? Because then you catch the bad cases also, very bad cases also. So based on how your epsilon and how your delta changes, the number of queries that the auditor has to ask to give its decision will change, and I'll show that. So this is the protocol in which the auditor and the data scientist communicate. The auditor queries a new point from the data scientist, like it picks a query and then asks the data scientist. And then the data scientist returns a label and an explanation to the auditor. So explanation here is auxiliary information. You can replace it with something that makes sense for your auditing property. But right now I'm using explanations. And then the auditor, like based on the results that it has gotten so far, the auditor decides whether it is ready to give an answer or not, right? If it is ready, then it gives yes or no, whatever. And then if it is not, it continues to the next time step. And what I was saying earlier was that based on this epsilon and delta, the number of queries, the T, will change. Yeah, and the point now is to design algorithms such that this guarantee is satisfied. So what are the degrees? Like how will you design different algorithms? One is like the auditor queries a new point. So how does it pick a new point as 1 degree of freedom? Then the data scientist returns an explanation. So what if you have another auxiliary information? And third is auditor decides whether to stop or not. So how does this decision happen? Like these 3 are the degrees of freedom by which you can design different algorithms. Yeah, and this gives you like the decision of whether to stop or not gives you something called the query complexity. And the query complexity changes with epsilon and delta. So if you want a very, very good auditor, you'll obviously have to query a lot. Yeah. Any questions till now? Okay, I'll just go ahead. So like we have the protocol and we have our guarantee, and I will, using these, now I'll define an auditing algorithm and a process for auditing feature sensitivity. So feature sensitivity is like whether a feature is being used to make a prediction or not. This is what we call feature sensitivity. So to define this, we have a feature of interest. For example, it can be gender, or it can be like anything that you want to audit for. And then using this feature of interest, we create pairs. So pairs are a pair of samples where all features are same except the feature of interest. So here we have 5 features. So all features are 4 features are the same for these 2 samples except the gender. And then we have responsive pairs, like pairs wherein the decision changes are called responsive pairs. So that is because like just based on because all the features are the same, right? So just based on this feature of interest, which is gender, model changes its decision. So it responds to the change in gender. That's why they are responsive pairs. Yeah, and now if we to define auditing property, we will use responsive pairs. So auditing property is basically, what do you want to know? Whether the model is sensitive to the feature of interest or not, right? Equivalently, it can be written as, do there exist responsive pairs with respect to the feature of interest, right? So if responsive pairs exist, then it means that model uses this particular feature, right? So you can write S of H as the fraction of responsive pairs, or the probability that a pair is a responsive pair. That is your score function in this case. Now, like, say I don't want to use all the stuff that I talked about earlier. Like, what's a really simple baseline that you would do using pairs? What you can do is you randomly create pairs, right? And then query. And as soon as you get a responsive pair, you know that the model is using that feature, right? So it can directly give you an answer. You don't need to use any of those stuff that I talked about. Now, the problem with this is that it's inversely proportional to epsilon. So if you have very less number of responsive pairs, since you are querying randomly, you would need a lot of pairs to find that responsive pair. So if there's only one, you will probably have to look for all the pairs that exist. And this problem is occurring because it's not picking pairs like based on something, right? It's just randomly picking pairs. It's not utilizing any of the structure of the hypothesis class, and it's not even using explanations. So this algorithm, like picking a pair randomly and querying, this will be the same whether it's a linear classifier or if it's a CNN or anything, it's going to be the same, right? So that's why it's not exploiting structure of the hypothesis class, and it's not even using auxiliary information like explanations in our case. So next we are going to see like how can we use my protocol that I talked about and the structure of the hypothesis class and explanations to give you better queries, better query complexity. Yeah, I think I don't need to talk much about this slide in this group at least. So given X, I'm just trying to talk about the two kinds of explanations that I use in the paper. So one is counterfactual, the other is anchor. So counterfactual is given a point X, what's the closest point with a different label? That is counterfactual explanation. And anchor explanation is given a point X, give me a hyperrectangle around X where the label is the same. I'm simplifying it. There's like precision and coverage parameters associated with anchors. But right now, like given a point X, give me a rectangle around X where everything has the same label as X. So these two are the different explanations. And now, like if I consider linear classifiers to be my hypothesis class with counterfactual explanations, then the surprising result that we have is only one sufficient query is sufficient to audit. So you can pick any query randomly, and that will be enough for you to audit. Like that will give you the answer directly. So if you think about feature sensitivity, like in linear classifiers, you have a linear classifier with weights, right? And those weights, if the weight of feature I, which is your feature of interest, if it's 0, then you know that it's not being used, right? It's simple. And in this particular case, what you're actually trying to find is whether the weight of that feature is 0 or not. So if you pick any query on like one side of the linear classifier, and then like the counterfactual is going to be like the one perpendicular to it, to the linear classifier. So, and the difference between like this is X bar, which is the counterfactual explanation. So X minus X bar is parallel to the weights. So in that case, like if wi is 0, then x minus x bar I is also 0. So that's how, like, you just need one query. You can pick any query randomly, and because of the nature of the classifier and the goodness of counterfactual explanations, you will just get your answer in one query. But with anchor explanations, we have a negative result. Like worst case, anchor explanations will not help you in improving your query complexity. You would need the same number of queries as active learning. But the good thing is that in average, like the average anchor explanation is not going to be worst case, right? So that will in fact help you, and we show that experimentally. Yeah,
Sure.
any questions?
I had a question. So just a clarification question. So you mentioned that in the previous slide that if you can find even one responsive pair, you would say you can stop and say yes. So my question is that, so are you giving like no leeway to the model that even if there's one responsive pair among, there could be millions of queries, you'll say the model is unfair? Is that thing you're saying?
So here I'm saying is the number of queries that you need to ask will grow inversely with the grow inversely with the badness of the model. So like if the model is only little unfair, then to find those pairs where it is unfair is going to take you a lot of
Very
samples in
expensive.
the worst case.
Right. And if you find any such example, would the auditor say that the model is unfair, or will they like estimate that something?
Yes, so like if the model finds even one responsive pair, then it knows that the model like for example in linear classifiers, then it would know that the wi is non-zero, right?
Yeah, for linear classifier, it's like that's definitely a case, because you can also, yeah, for, as you said, for linear classifier, and I think you'll talk for other hypothesis classes, so I'll wait for that. So
I'm not talking about other hypothesis classes in this case, but like if you can imagine, like for a neural network, right? It's going to be more complicated than just weight of ith feature, right?
correct.
And in that case, like like there is no closed form thing which you can see. Like in linear classifiers, you can say that the wi is equal to 0. That means non-responsive, whereas wi not equal to 0 means responsive, right? But there's no clear-cut such form that you can say for neural networks, as far as I know, right?
Correct. Yeah.
So in that case, if you use this algorithm, then like if you get a responsive pair, it still means that the model is using that feature somehow, right? Because you
Correct.
see, like all other features are the same.
Yeah.
Right. So the only difference in feature is the feature of interest. Hence, the model has to use that feature in order to give a responsive pair. And the goal of the auditor is not to say that, the model is the goal of the auditor is objective, right? So if it finds even one responsive pair, that means that the model is using that feature of interest, and hence it is unfair. Like it does not care if you have lots of if you have lots of responsive pairs or you have only little.
Okay, so it's literally binary. Even if it look, so a very unfair model and a very like
less unfair.
a less unfair model will be, in this case, both will be a yes unfair, right? That's
Yeah.
okay. That's all the question was. Thank you, Chhavi. You can come. Sorry.
Okay. Any more questions? Okay, so yeah, I was thinking about the question a little bit more. So in that case, like the auditor will give its decision, like it is, so you can change like from binary variable to like real values and stuff like that. So in that case, you can tell like how much unfair the model is, and then it's like the policy's decision or the government's decision to decide whether or not the model should continue, and so on. Yeah. Okay, so like I've written this very like in one slide, like what are the main results, but this is one of the main results of the paper. Next, what I will show is something about the protocol in general. So this is it about auditing feature sensitivity. If you look at our protocol, this thing, if you guys know something about active learning, you will clearly see that this is very similar to active learning. So in active learning, what happens is the goal is to learn the hypothesis, like there is an active learner and there's an oracle. And the goal of the active learner is to learn the hidden model, right? And how it learns the hidden model is by actively picking up some queries to get labels for from the oracle, and then it learns the hypothesis. So this is very similar. If you look here, like auditor also picking queries, and then it's getting the labels from the data scientist who can be the oracle now, and then it makes some decision. But I will show in the next few slides like how it is different from active learning. So yeah, first I'll start with similarities. So if you don't use explanations, or the explanations are useless, like in Anchor's case, the explanations were useless. So in that case, it can sort of reduce to active learning because you just get labels from the data scientist, right? And then, so I didn't discuss this in much detail, but even in our paper, like we maintain a search space of some sorts, and the search space is over hypothesis. And with each query that we get labels and explanations for, we like reduce the search space. But yeah, so that is like the similarity, that we also have a search space over hypothesis. And here we also assume that the data scientist is truthful. So we have a truthful oracle. That's why it's like called the oracle in active learning. And that's one more similarity. Yeah, and we have one more result, which says that if there exists a membership query active learner, so membership query is a kind of active learning. So if there exists a membership query active learner that learns the hidden model in T queries, then it can also audit in T queries. Yeah, so if you know what is the H bar, if the auditor comes to know what is H bar exactly, then the S of H bar will tell you to what extent it is fair or unfair, or what is the accuracy and so on. Like this is a very theoretical result, like because once you know H bar, you still need to do some computations in the real world to find what is S of H bar, right? So this is like the theoretical result. But anyway, yeah, now I'll discuss differences with active learning. So as I mentioned earlier, the goal of active learning is to learn the H bar, right? But unlike active learning, in auditing, the goal is not to learn H bar. Like you don't care what is the hidden model. You just care about giving the right auditing decision. And that like learning might be one route to giving that decision, but that may not be the only route, right? So that's one difference. And another difference is searching for hypothesis, right? In auditing, we are not searching for hypothesis. And one example is in the guarantee itself. Like suppose, since we have a search space over hypothesis and we are reducing the search space each time. Now, suppose at a point, all the hypotheses in the search space have S of H equal to 0. All of them have S of H equal to 0. So you can directly give a decision saying no, right? Like you don't need to find what is H bar, because everything in the search space, which includes H bar, has a S of H equal to 0. So you can directly give the decision. So you don't need to learn the hypothesis. And also the search space, like in our paper, the search space is over hypothesis, but that need not be the case. You can have a search space over responsive pairs or responsive pair and hypothesis and so on. Yeah, and we also have a discussion on untruthful data scientists. So if that can actually correspond to like active learning with noisy labels and so on. But yeah, that's like if you want to differentiate between pure active learning and auditing, you can say that the data scientist does not have to be truthful. Right. So that is what I was talking about. So I said that auditing might be a route, learning might be a route to auditing, but it may not be. And one thing I want to point out here is in linear classifiers with counterfactual explanations, what you are getting is a scaled version of the weights. And you don't need the bias, right? So in a way, you have only partially learned, like you're not completely learned the H bar, because what you know is just a scaled version of the weights, and you don't even know the bias. So you're not actually learning the hypothesis completely. And I had a discussion with somebody and this interesting point came up. So I can ask, like, instead of asking for the query, I can just ask the data scientist, like, what is the inner product of your weights with, say, a one hot vector where the one is on the feature of interest, right? If this dot product is 0, then you know that the weight is 0. So like you don't need to like ask a query in the traditional sense. Like you could ask like something else probably to get the answer. Yeah, and another difference is that we use explanations like counterfactual explanations that reduce the query complexity by a large amount. Yeah, any questions? Like these were the, like, I think I'm not sure if people here care about active learning, but this is very similar to like active learning, and that was one of our inspirations also.